Hello everyone, and welcome to what will be our last lecture for number theory. The last two lectures we've been talking about modulo arithmetic, and we look at some special theorems. Last time we had some elementary algebraic properties of congruences, like if A is congruent to B mod n, and B is congruent to C mod n, then A is congruent to C mod n. Or if A is congruent to B mod n, then A plus C is congruent to B plus C mod n, and so forth. Now, I guess we need to look at some theorems that are not quite so obvious. If we have, just for example, let's say that we have A plus B congruent to A plus C mod n. Is it necessarily true that B is congruent to C modulo n? Well, let's see. That we have a property that says essentially that if B is congruent to C, if A is congruent to B mod n, then we can add the same number to both sides of the congruence, and the congruence still holds. So we could add C plus A is congruent to C plus B mod n. So we took a congruence, added the same number to both sides, the congruence is preserved. So can we use this idea to show that if A plus B is congruent to A plus C, then B must be congruent to C? Well, by the property that we just listed here, I would say, okay, take negative A and add it to A plus B, and add negative A to the other side too. And addition's associative. So essentially, we could associate these two things together first. And we could associate these two things together first. This is just 0. So what we have is B is congruent to C mod n. So in other words, that we can add or subtract the same number from both sides of a congruence, and the congruence still holds. So if A plus B is congruent to A plus C, then yes, B is congruent to C modulo n. Now I'm bringing out that point because the same kind of cancellation property does not hold for multiplication. Let's see. If A times B is congruent to A times C mod n, does that imply that B is congruent to C mod n? And apparently it doesn't, because if it did mean this, then we wouldn't have to have theorems like this and theorems like that. So we'll answer this question with a resounding no. The multiplication cancellation properties don't hold for modulo arithmetic. If AB is congruent to AC mod n, that does not imply that B is congruent to C mod n. And let's look at a counterexample. Oh, let's make it an easy one. Oh, well, here's a good one. Except I'll use mod 10. 10 times 3 is congruent to 10 times 7 mod 10. And that's true. This is 30, which is congruent to 0 mod 10. This is 70, which is congruent to 0 mod 10, because 10 divides both of these things. But what happens if I cancel a 10 from each side? I have 3 congruent to 7 mod 10. And this is definitely not true. That is not true. And to see that, just take 3 and subtract 7. 3 minus 7 is equal to -4. And that is not congruent to, and that is not equal to k times 10 for some integer k. So here's an example to show that if we have A times B congruent to A times C, and 10 is our A here, and 3 is our B, and 7 is our C. We have AB congruent to AC mod 10. We can't cancel the 10s from both sides and still have a congruence. So I guess the question now is, are there any occasions where we do have a congruence like this, where we can cancel the common factor from both sides? And these two theorems tell us when this is possible. We have CA congruent to CB modulo n. And apparently we can cancel the C's from both sides and still have a congruence modulo n if C and n are relatively prime. They have no common divisors other than 1. So if CA is congruent to CB mod n, and C and n are relatively prime, let the good times roll. We can cancel the C's from both sides. Now, with that in mind, Do we see why we couldn't cancel 10 here from both sides? 10 is our A, and what's our N down here? Oh my goodness. 10 is also our N. So, yeah, greatest common divisor. You know what? I just messed this up. Forgive me. I didn't label things correctly. Let me do it again. 10 is our C. 3 is our A. 7 is our B. Okay. We've got all the main characters properly assigned now. We can't cancel the C's from both sides because C and N are not relatively prime. As a matter of fact, C is equal to N. And the greatest common divisor of C and N is 10. It's not equal to 1. So we can't cancel the C's. So that's what went wrong in this example. Here's C, that's 10. And, oh, wait a minute, this is a different example. Okay. Well, let's look at that. Let's look at that. In the example that we just did, 10 was C, and 10 was also N. The greatest common divisor of the two was not equal to 1, so we couldn't cancel the C's. Let me get rid of this example now. Ten times 3 is 30. 10 times 10 is 100. And 10 times 3 is 30, which is 2 mod 7. 10 times 10 is 100. Let's see, 7 goes into 100 14 times, remainder 2. So this is 2 mod 7 also. Well, did we just get lucky here or what? If we cancel the 10s from both sides, we get 3 is congruent to 10 mod 7, and that's true. We know it's true because if we subtract 10 from 3, we get negative 7, which is equal to some integer times 7. Now, why did this work when in the previous example we couldn't cancel the 10s from both sides? Well, let's diagram our congruence, and let me make sure I do it correctly this time. Our 10 is still C, and A is 3, B is 10, and 7 is our N. The greatest common divisor of C and N, that's 10 and 7, is equal to 1. They have no common factors other than 1. And since the greatest common divisor of C, the common factor, and n, the divisor, is equal to 1, we can cancel the common factor from both sides. So this does imply that, tell you what, let me write the 10 in anyway. Let me write the 10, just so with emphasis, I can show that I'm canceling the C on each side. And the reason I can cancel C on both sides is because the greatest common divisor of C and n is 1. C and n, 10 and 7, are relatively prime, so I can cancel 10 from both sides. Now, let's look at another example. Well, let's look at this example. What the heck? Let's look at it again, but let's apply this theorem. Let the divisor be a prime number. Essentially, this theorem is just a special case of the first one. But let's look at it. Using this second theorem, why can we cancel the 10s on both sides? The criterion in this second theorem is that the divisor does not divide the common factor. So the divisor, 7, which is prime, does not divide the common factor 10. And that gives us the right to cancel the common factor from both sides. Okay, let's look at some more examples. Suppose we have 21x congruent to 21y mod 3. Does this imply that x is congruent to y mod 3? What do you think? Both of our theorems apply. Our divisor is prime. So let's see. Here's C, here's A. Here's C, here's B. And this is N. Here's what we observe. greatest common divisor of C and N. So that's going to be C and N. And contrary to what I said, C is 21. Greatest common divisor of 21 and 3 is 3, and not 1. So 21x congruent to 21y mod 3 does not imply that x is congruent to y mod 3. And let's look at a case in point. Or a counterexample. (21 times 5 is not congruent, I hope, to 21 times 10 mod 3. Now let's identify the main characters. Our common factor is C. So 5 is our A, 10 is our B, and 3 is N. And I better rectify what I've written here. These are actually congruent. Change that to congruent. They have to be because 21 is a multiple of 3. In other words, 3 is a divisor of 21. So 21 is congruent to 0 mod 3. So essentially, we're multiplying both sides of this equation by 0. So we have 0 congruent to 0 mod 3. Yeah, that's true. But here's where the negation comes in. We can't cancel the 21s. We can't cancel the 3s. 5 is not congruent to 10 mod 3. 5 is congruent to 2 mod 3. Because 5 divided by 3 leaves a remainder of 2. And 10 is congruent to 1 mod 3. Because 10 divided by 3 leaves a remainder of 1. So in this example, 21x congruent to 21y does not imply that x is congruent to y mod 3. We can't cancel the common divisors. And the reason we can't cancel the common divisors is because the common divisor and we can't cancel the common factors. And the reason we can't cancel the common factors is that the greatest common divisor of 21 and 3 is not equal to 1. Now, if we have something like this, where the common factor and the divisor n are not relatively prime, does that mean that this that we can never cancel the divisors? Not necessarily. But sometimes we might be able to cancel the 21 and we get something that's true. Other times, that's not the case. And if we can't cancel the common factor all the time, then we don't want to do it. So the only time we can cancel the common factor is when the common factor and the divisor n have no common factors. The common factor 21 and the divisor n are relatively prime. If that's the case, then we can divide both sides by the common factor. An integer a Forgive me. Let me get my definition straight. Okay. Those of you who have had abstract algebra are probably familiar with this concept. A zero divisor modulo n. So A is a zero divisor or a divisor of 0 modulo n. If A is not congruent to 0 mod n, but there's some other integer which is also not congruent to 0 mod n, such that their product is congruent to 0 mod n. And I guess a remark would be appropriate here. If A is a zero divisor mod n, because there's some integer b such that AB is congruent to 0 mod n, then B is also a zero divisor mod n. these two things come in pairs. So let's look at an example. A equal 3 and B equal 2 are zero divisors mod 6. And A is not congruent to 0 mod 6. And B is not equal to 0 mod 6, or B is not congruent to 0 mod 6. But let's see, what's the significance of 6 here? 6 is just A times B. 6 is 2 times 3, or 3 times 2. Their product is congruent to 0 mod 6. So let's see, what would be another way of stating our original theorem that tells us exactly when we can cancel? We can cancel the factors of C on both sides of a congruence exactly when C is not a zero divisor mod n. see, is 4 a zero divisor mod 12? Is there some other number that's not congruent to 0 mod 12 that we can divide, that we can multiply 4 by and get 0? Yeah. Four is a zero divisor of 12. 3 is a zero divisor mod 12. So 4 is a zero divisor mod 12. So we can't cancel the 4. Okay, let's look at another example. Is there any number not congruent to 0 mod 15 that we can multiply 4 by to get 0 mod 15? No, there isn't. So 4 is not a zero divisor, mod 15. So we can cancel the 4s on both sides of the equation. Now, could we have done this differently? Yeah. We could say 4 and 15 are relatively prime. So we can cancel the 4 from both sides. Just a homework assignment to get us ready for the final. Some good stuff here. Should I stop here? Almost. I'm going to give you just a little bit more, but not much. Okay, I'm back with a couple of more theorems that I'm going to throw at you. These are application theorems. We're not going to derive their proofs. We're running short of time in this semester, but these are some things that would be good for you to see. In this first theorem, we let capital N be some natural number. And this is the base 10 expansion of capital N. Now, notice that what we have really are just each of the place value digits of n. A sub m times 10 to the m, a sub m minus 1, 10 to the m minus 1, so forth and so on, plus a sub 2, 10 to the second, a sub 1, 10 to the first, a sub naught, 10 to the 0. Well, what is this really saying? Now, the way I have it written here, am I denoting a product? No. This is not a sub m times a sub m minus 1 times a sub m minus 2. That's not what this represents. This is the base 10 representation of capital N. So in other words, this is the ones digit. This is the tens digit. This is the hundredths digit, and so forth. These digits are just placed side by side. So this is the base 10 representation of capital N. And what does it represent? It represents a sub m times 10 to the mth, a sub m minus 1 times 10 to the m minus first, and so forth. Well, here's the theorem. If 9 is a divisor of n, then it's also true that if we just take the sum of these digits, not the sum of the digits times their respective powers of 10, but just the sum of the digits themselves, a sub m plus a sub m minus 1 plus a sub m minus 2, and so forth. If we just take the sum of these digits, then 9 has to divide that sum also. I'll say that again. If 9 is a divisor of capital N, and 9 divides the sum of the digits of capital N. No, I didn't say that right. If 9 divides capital N, then 9 will also divide the sum of the digits of capital N. And this goes the other way too. It's an if and only if proposition. If 9 divides the sum of the digits of N, then it's also true that 9 is going to be a divisor of N itself. So let's put that to the test. So N equals 3897, 42153. Is 9 a divisor of N? If it is, then 9 will have to divide the sum of these digits. And if 9 divides the sum of these digits, then that means that 9 is a divisor of N. See, 3 plus 8 is 11, plus 9 is 20, plus 7 is 27, 31, 33, 34, 39, 42. And let's see, does 9 divide that? I don't think it does, no. 42 is 9 times 4, or let's say 4 times 9, plus a remainder of 6. Nine does not divide the sum of those digits, so 9 does not divide the number 3897, 42153. So 9 does not divide N. Okay, another example. Consider this number. Does 9 divide this number? Let's check. We'll take all of the digits and add them up. 4737, 42567. Okay. So we have 11, 14, 21, 25, 27, 32, 3845. So 9 divides the sum of the digits. Since 9 divides the sum of the digits, it turns out that 9 divides the number itself. Now, something that I should be mindful of, this theorem that I'm applying is such that this is the base 10 representation of the number n. If I have the representation of n in a different base, all bets are off. This goes for base 10. Now, let me throw another theorem at you. This theorem also works for 3. If we add up the digits of the number n and 3 divides that sum, then 3 divides the number n itself. And if 3 divides the number n, then 3 is also going to divide the sum of the digits. So, let's take a look at this. Consider n equal 389,742, 153, what happens when we add the digits? Let's see, did I do that right? 389,742, 153, yes. 11 plus 9 is 20, plus 7 is 27, plus 4 is 31, plus 2 is 33, 34, 39, 42. We add those up, and we get 42. And that's equal to what, 13? No. Let's see, 14. Yeah, 14 times 3. So since 3 divides the sum of these numbers, since 3 divides the sum of the digits, 3 divides the number itself. Now, one more example with this trick. Okay. Does 3 divide n? Well, let's take the digits and add them up. Let's see, did I get them all? 247, 15630. And that's 6 plus 7 is 13, 14, 19, 25, 28. When we divide 28 by 3, we get a remainder of 1. So essentially, we found out that 3 does not divide the sum of these digits. Three does not divide the sum of the digits. So 3 does not divide the number itself. One more divisibility theorem that I'm going to throw at you. Again, we have the base 10 representation of a number n, capital N. And here's what we do. Starting with the ones digit, we add and subtract alternately the digits until we get to the mth digit. A sub 0 minus A sub 1, plus A sub 2 minus A sub 3, and so on. I'm writing it this way with the digits in reverse order just because it's easier to state in the general case. But you might be asking, well, why did he do it in reverse order? I did it in reverse order only because it makes it easy to state the general case, where we don't know exactly how many digits the number has. Now, if I'm looking at a number, I know how many digits it has. Can I start at the mth digit and go to the ones digit and just add and subtract the numbers alternatively or alternately? Yes. I could go like this. A sub m minus A sub m minus 1 plus A sub m minus A sub m minus 2 minus A sub m minus 3 and so forth. I can do that. Add and subtract the digits alternately, starting with the largest digit. I can do that. The point is, if we take the digits of n and add and subtract successive digits alternately, and 11 divides that sum, then 11 is going to divide the number n also. And it works the other way around. If 11 divides the number n, then if we add and subtract the digits of n alternately, 11 is going to divide that sum as well. So I don't necessarily have to start with the ones digit and work my way to the nth digit. The point is I just have to start either at the nth digit or the 0th digit and just add and subtract the digits alternately. So let's look at an example. Oh, let's see. Let's see, 4737. 7352. 47. 374. Does 11 divide n? Let's check. We can start here. We can start here. It doesn't matter. So let's say 7 minus 3 plus 5 minus 2 plus 4 minus 7 plus 3 minus 7 plus 4. Did I get them all? 735, 247, 374. Yep, I got them all. And now what do we get? 4 plus 5 is 9, minus 2 is 7, plus 4 is 11. Minus 7 is 4, plus 3 is 7. minus 7 is 0, plus 4 is 4. Eleven does not divide 4. So 11 does not divide 7 minus 3 plus 5 minus 2 plus 4 minus 7 plus 3 minus 7 plus 4. And because of that, 11 does not divide the number itself. 7, 3, 5, 2, 4, 7, 3, 7, 4. So 11 does not divide n. Let's look at one more example. Last example. Here's our number n, base 10 representation. Does 11 divide n? Let's check. And we add up the digits. We add and subtract the digits alternately. And it doesn't matter if we start here or if we start in the ones place. It's going to work out the same either way. Alternately, we add and subtract the digits. Now, let me make sure I did this right. 389, 742, 353. Okay. So 3 minus 8, negative 5, plus 9 is 4, minus 7 is negative 3, plus 4 is 1, minus 2 is negative 1, plus 3 is 2, minus 5 is negative 3, plus 3 is 0. Okay. And that equals 0 times 9 with a remainder of 0. So in other words, whoops, 9 my foot. 0 times 11. 11 divides 0. So we'll make this observation. 11 divides this sum, 3 minus 8, plus 9 minus 7, plus 4 minus 2, plus 3 minus 5, plus 3. So 11 has to divide the number n itself. 389, 742, 353. So yes, 11 does divide n. And having been exposed to this material, that we should be able to do the exercises on page 73. Primarily, they involve testing for divisibility by 9, by 3, by 11. And that concludes the course. This is the final lecture. The final exam will be coming out shortly. I'll give you some time to work on these homework exercises first. And during final exams week, I think maybe we should set a time when I'll be open for questions and answers on homework or other questions. As long as they're not questions directly pertaining to the final exam. And I'll email you and just see what questions you'd like to have answered, and then I'll present them much in the same format that I just presented this lecture. I hope to see you again. Some of you are going to be graduating now. And if you do, I guess they will have your public graduation ceremony at the end of the summer, the same time that they have graduation for those graduating in the summer. So if you're graduating spring semester or summer semester, and you're going to attend the public graduation, I will be delighted to see you there. If you're not graduating right now or this summer, I'll look forward to seeing you in person this fall. You've been a wonderful bunch of kids, you have. Each and every one of you, I've enjoyed having you as students and as a class, and I really do look forward to the time when I'll see you again face to face. Seriously, I say this with a smile, but also in utmost sincerity. The pleasure's been mine.